Hello and welcome back everyone to our Physics 8A live stream. This week we're going to continue with solid rotation or torque with part 2 of 3, which is going to focus on kinematics and effectively Newton's second law for rotational motion. So if we recap real quick, a couple of things. The first thing is that I said I'd like to do the torque chapter in 3 different parts so that we can compartmentalize each one and kind of move through them in a logical way where we learn something and then we build on it and we keep building. And it's in a way where, for example, last week we started with torque net equals 0. This week we're going to upgrade to torque net equals I alpha. So that was my decision to break it up in this way, which is not necessarily the way that it was covered in lecture. But again, the point is to say, well, when we started with forces, we said F net equals 0, then we said F net equals ma, then we did work and energy. Here it's the same idea. Last week we talked about torque net is equal to 0 and the equilibrium condition, and we saw that F net x and F net y being 0 wasn't enough. We had to add torque net equals 0 so that we could describe something in equilibrium. But of course, not all things in life are in equilibrium. So this week we're going to focus on a couple things: rotational kinematics, and then we're going to talk about torque net equals I alpha, which of course the torque net part, we already know what that is. So we just have to focus on the new part, which is I alpha. I being the moment of inertia and alpha being the angular acceleration. And effectively this is like F net equals ma, but for rotational motion. So it's going to give us the angular acceleration, which will be useful to answer questions about kinematics and so forth. So with that said, that'll be this week, and then next week we're going to focus on rolling without slipping and energy, which this will revisit torque net equals I alpha a little bit. We'll see how. And then we'll focus on conservation of energy for a cylinder or sphere, for example, rolling without slipping down an incline, things of that sort. So today let's start with kinematics and just do a quick recap of kinematics and then torque net equals I alpha before we move on to some practice problems. Okay. So just as a reminder, I'll gray it out because we don't really, it's not what we're focusing on today, but kinematics goes back to the very beginning of mechanics, right? And where we said, well, if I write it along the x direction, x as a function of time is going to be 1/2 ax t squared plus v naught x t plus x naught. And then along with it comes vx of t, which is just axt plus v naught x, right, which is the derivative of x with respect to time. And these two equations kind of go hand in hand. This is the derivative of this, so they're related. And they're functions of time, right? So if you tell me time, I can find position and velocity. But the point is, it is a function. So there's an input, which is t, gives you an output, either x or v sub x. Now then there's a third equation, which is, it's not really a function, it's an equation. It's a relationship between 2 points in the motion, one that you'll call initial, one that you'll call final, where we say that v final in the x direction squared is v initial in the x direction squared plus 2 a sub x delta x. Now this one no longer involves time. It comes from combining these two and eliminating time between them. And it's a great equation if you don't care about time. If you just want to know how fast you're going, given a certain acceleration and a certain displacement, you can figure out v final x. Maybe you start at rest and v naught x is 0 or something like that. But it's a great equation if you're not looking for time. So it's not always useful, and it's also not a function, right? It has no input. It's a relationship between quantities where you have to decide what is initial and final, and then you write the relationship between those two states. So that is for motion along x. And of course, we saw in projectile motion, you could write the same thing along y. You could have both motion along x and along y at the same time. That is projectile motion. And so hopefully by now we're comfortable enough with this that it's nothing new and we understand how these things work. And I put them here because next to them I'm going to write the kinematic equations for rotational motion. Now, rotational motion is a very different type of motion. Okay, so we don't have motion in a straight line. Instead, you have rotation about a fixed axis, or sometimes called a pivot point. But the idea is that in the case of rotational motion, you're going to have, let's say this is a turntable viewed from above. Okay. And you put a sticker here and a sticker here on the turntable. Two red stickers, one in the middle, one at the edge, right? And then this thing is going to rotate. So the turntable is turned on and it rotates, let's say counterclockwise, just to pick something. And the thing is that this point here on the outside has to travel a circle this big in a certain amount of time in one revolution. This one has to travel a circle smaller than the outer circle in the same amount of time within one revolution. So the reality is that this point, as far as linear speed goes, travels faster than the point in the middle. In fact, each sticker that I could put on the turntable like that is going to have a different v, right? So that's not very convenient to think of things in terms of v. Plus, it doesn't really make sense. By the way, this would be 2v if this point is really at the middle. It doesn't really make sense because, well, that's true right now if I look at it. Yes, there is linear motion upward just this moment, but the reality is that that's not really the overall motion. The overall motion is that these points are going to go around together like this, the turntable, right? So they're going to cover the same amount of radians, the same angle, in the same amount of time. So it's going to be a lot better to describe them in terms of angular velocity and angular position than it is to describe in terms of linear velocity v, or even linear position x doesn't even make sense. I mean, x is going to change all the time as you go around in a circle, and it's really not the best way to go about it. So the point is, we introduce these quantities, which I'm going to set this as my reference. This is going to be theta 0, which I can make 0. I don't have to, but it's pretty common. And I'll say, okay, well, that's where the stickers were before I turned the turntable on. Once I turn it on, they start to rotate counterclockwise around with the turntable, and they sweep through a certain number of radians overall. Okay? And at any given moment, if you tell me what the angle is measured relative to my reference, so if you tell me what this angle is, theta is a function of time, well then that's all I need to know. Because if I can locate this line here, I know that in the middle there's a sticker, and I know that at the edge there's a sticker. Okay? So I only need to know theta to know exactly where these guys are as they rotate around the turntable. So theta t is going to be our angular position. Okay, it is the angle that gives me my position. It tells me where these stickers are in the motion. Now, of course, where they are and how fast they go from here to here has to do with how fast the turntable rotates. So that would be an angular speed omega. Now, I might call it omega of t because perhaps it's not constant, but omega of t is going to be your angular velocity. Okay, now by the way, theta of t is going to be in radians. It tells you the total number of radians that you've swept through in time t, and then omega t is going to be in radians per second, and that's going to tell you at any given moment how many radians per second are you sweeping through. So how fast are you spinning, really? And of course, just like Vx here can change because of linear acceleration a sub x, well, angular velocity can change because of angular acceleration. Now, it's always hard to draw angular acceleration. We don't really know. Like, you could draw it clockwise or counterclockwise. The point is, let's assume that I draw it like this, just to make a point. Then it would be in the same direction as omega. It's going to speed up omega could go the other way and slow omega down. And note that I didn't write alpha as a function of time because we're going to make the simplifying assumption, just like we did here, that the acceleration, in this case the angular acceleration, is constant. Right? By the way, these equations here are only valid if a sub x is constant. Okay, we talked about that before. So here you're going to get angular acceleration. That's going to be in radians per second squared. And it will tell you by what amount omega changes every second. So if you have 5 radians per second squared, you're saying that every second omega increases by 5 radians per second. That's what acceleration represents. Okay? And then of course, you know, the similarities continue where, well, what do you think omega is? Omega is how fast theta changes with time. Okay, well, so then omega is equal to d theta dt, just like v sub x is dx dt. And then alpha is going to be d omega dt. And so my point here is just to say that the relationships between theta and omega, and then omega and alpha, are the same as between x and vx, and then vx and ax. We assume that the angular acceleration is constant, just like we did for the linear acceleration a sub x. And so it stands to reason that we would get equations that look very similar to these equations that I put here just as a reminder. Okay? And so in the rotational world, we're going to get position, which is given by theta t, is going to be equal to 1/2 alpha t squared plus omega naught t, that's the initial angular velocity, omega naught, that is how fast you're spinning at t equals 0. Could be 0 if you're at rest, it could be whatever. And theta 0 is your reference. Now usually we choose 0 because we want theta t to represent the accrual of radians through which you swept over time. But theta naught does not have to be 0. It could be whatever constant you want. It's just that then this will measure the accumulation of radians as time goes by. Omega t is going to be the derivative of this, which is going to be alpha t plus omega naught. And then we also have, by combining the above two, a similar equation that eliminates time. Omega final squared is going to be omega 0 squared plus 2 alpha delta theta. There we go. So these are my kinematic equations. Now, I didn't want to, again, re-derive everything from scratch and spend a whole lot of time on kinematics, but I also didn't just want to write this and say, hey, it's the same thing as this. So hopefully this is a nice little middle ground where we can say, okay, we understand kinematics from before. Here we have kinematic equations that look very similar. They're going to work the same way. They just represent different quantities because we have a different type of motion. But we'll do a problem just that is pure kinematics. And you'll see that whatever you're used to doing for linear kinematics is going to be the same here. And it's not going to be that bad at all to make the transition, right? So something to keep in mind, these kinematic equations are important. We don't tend to focus on them as heavily as we did before, because before we did projectile motion and all of that. But you have to know that they exist, and you have to know that they will give you theta, omega, and presumably alpha, unless you solve it differently using torque net equals I alpha. But they give you position and velocity basically at all times for your rotating object, be that a rotating cylinder or a ball rolling without slipping down an incline, whatever. But there is going to be kinematic equations for that type of motion, which makes sense, right? So each motion has its own kinematic equations, and these are them for rotational motion. So the reason I started with kinematics is that I wanted to define alpha before it showed up in torque net equals I alpha, because the goal is to progressively move through the chapter and, do it in a way that it makes sense. It's, we gain knowledge as we go, and then we go a little further every time. So now that we know what alpha is, we understand it's the angular acceleration, in other words, how fast omega changes every second, we can talk about finding omega using torque net equals I alpha, which is basically Newton's second law, but for rotational motion. Okay, so I'm going to write Newton's second law. And everybody understands if you just write that. In theory, we should call it Newton's second law for rotational motion, but that's a lot of words, and not everybody is willing to say that every time. Just say Newton's second law. Okay, so Newton's second law is very simple. It's very similar to F net equals ma. It simply is torque net is equal to I alpha. Now we know what torque net is because we did that last week. Torque net is the sum of all the torques, right? If you have 5 forces acting on your object, you have 5 torques. You go evaluate each one with respect to a given pivot, and then you add them all together. Some will be positive, some will be negative, some will be 0, and then you get your net torque. So we did that last week. So the left-hand side of the equation is nothing new. The right-hand side is kind of new, kind of not. I mean, we just explained what alpha is and why you would need it. It's to get your kinematic equations. Question is, what is I? So we need to talk about I, because the moment of inertia is a little tricky, and sometimes, you know, we don't spend enough time on it up front. So we're going to talk about moment of inertia, really, and I don't need to say more than torque net equals I alpha for this part, meaning that, you know, basically F net equals ma, when you were given that equation, that was absolutely not helpful. You're like, okay, cool, F net equals ma, now what? Well, now you have to go do, you know, 5, 10 problems to understand F net equals ma and in what context it is applied, how it is applied, and what it gives you. Most of the time acceleration, but not exclusively. So once you do that, then you have context. And when then someone says F net equals ma again, you're like, oh yeah, no, I know F net equals ma, and I did 10 problems, so I kind of have an idea of what I do with that, right? But it's the same thing here. I tell you torque net equals I alpha, so what? Well, so nothing until we do a few problems to see, okay, in the context of rotational motion, this is how you apply torque net equals I alpha, this is what it gives you, and then you'll be like, okay, I understand. Yes, torque net equals I alpha, but given all the problems that I've seen, I understand what it means and how to use it. So there isn't much more to say here when it comes to Newton's second law, with the following exception. And this is going to be important also next week when we talk about rolling without slipping. Okay. In the case of torque net equals I alpha, there's a very important thing to note, is that the net torque and the moment of inertia I must be computed with respect to the same pivot. This is really important. Okay, so as we're going to see, moment of inertia is defined with respect to typically an axis of rotation, but we could call it a pivot point, just like torque, right? For torque, you had to choose a pivot that determined what the torque of each force was relative to that pivot. Now, torque is the amount of rotation that you get from all the forces acting on your object, okay? And we're saying that it's equal to how hard it is to rotate multiplied by the angular acceleration, okay? So how hard it is to rotate is the moment of inertia. Well, you have to measure how hard it is to rotate with respect to the same pivot point that you computed torque about, because torque is how much rotation you get. So you can't say, well, I get this much rotation about this pivot, and then it's this hard to rotate this thing about another pivot. That makes no sense. But that's not necessarily made clear when we just write torque net equals I alpha. So just to be upfront about it, and we'll see in practice how we apply this and why it matters, you need to make sure that if you choose a pivot, it's not just for net torque, it is also for the moment of inertia. Okay, so then let's talk about the moment of inertia. Okay. Now, the moment of inertia is a measure of how difficult it is to rotate an object about a given axis. So we should probably write that down. That's the definition. So the moment of inertia I measures how difficult or how hard it is to rotate an object about an axis of rotation, or a pivot, same idea. Okay, but of course it's specific to the axis. If you compute I with respect to a different axis, you're probably going to get something else. Okay, it is a function of the mass and shape of the object. And of course, the greater the moment of inertia, the harder it is to rotate an object. Same idea with mass, right? The greater the mass, the harder it is to move something. That's the principle of inertia. If something is very heavy, you're going to have to put a substantial amount of effort into moving it. It just doesn't want to move. Well, if something is very bulky, very heavy, perhaps quite large, with a lot of mass far away from the axis of rotation, it is going to be hard to rotate. It just doesn't want to rotate. So that's going to be accounted for with the moment of inertia. A simple example in everyday life is you can swing a badminton racket or a wooden baseball bat, and obviously there is a difference. Right? It is harder to swing the wooden baseball bat. Not only does it have more mass, it has more mass further away, because the head of the baseball bat is where most of the mass is, whereas the handle of the badminton racket is where most of the mass is, and that's not a lot of mass to begin with. So there's a difference. You can try this one-handed swing of a badminton racket versus one-handed swing of a baseball bat. You will notice a difference. Well, that comes from the moment of inertia. Right? The baseball bat doesn't want to swing as much as the badminton racket because it has more mass, and the mass is also further away from the point about which you're trying to swing it. So let's go over moment of inertia. There's a few things we need to talk about. There's, first of all, the moment of inertia of a point mass, because nobody will give you that formula. It is expected that you know it. We can have a conversation about the other ones, the cylinders and the spheres and whatever. Those are typically given because it just doesn't make sense to memorize them all. But the point mass, that one is never going to be given. You need to know what it is. Okay, so the moment of inertia of a point mass. Okay, so remember, a point mass has no shape, no size, no front nor back, no top, no bottom. It is just a point of mass. It is this. And in some cases, we have objects that are small enough that we can just say, you know what, yes, it's not a point mass because that's a mathematical idealization. But as far as inertia goes, you can treat it as such, no difference. Like, okay, fair enough. Well, if that's the case, then here, let's say that I have a point mass. Let's say that it's rotating about this axis here. I'm going to call this delta. It's just how I call my axes. It's not really an official notation. And it's going around. Now, just to clear the air, how this is happening is not our responsibility. Like, we're not trying to build this in our garage. We're just saying, okay, you're telling me that there's a point mass that's rotating around this axis. I will tell you how hard it is to do that, right? So all you need to do is you need to tell me this distance, whatever this is. And if I know this distance, call it d, then I will tell you that I, with respect to delta, is simply md squared, which of course is in kilogram meter squared. That's the moment of inertia of a point mass. But I don't have to explain how I'm going to make this point mass rotate about the axis. That's the problem's problem. They will
give you a contraption or a situation where that's the case. You just need to know what the moment of inertia is. Okay. So that's for a point mass. That one will never be given to you. They have pretty much no reason to give it to you. I mean, maybe if whoever writes the exam is very nice and is in a good mood, but for the most part, you have to know the moment of inertia of a point mass. Okay. Okay, so then let's look at classic shapes or objects. Now these are going to have a moment of inertia that is typically given, because there is really no point in memorizing the moment of inertia of a hollow sphere, of a solid sphere, or of a cylinder or anything like that. That's honestly just a bad use of brain space. Like there's really nothing interesting about it. So I'm just going to draw a few just to make my point. There's a whole collection of them, right? There's the ring and or the hoop, and then there's the rod, and a few others that might show up and are going to be given on the formula sheet. But let's just draw a few of these because this is going to help me segue to the next point. Okay, so let's say that this is a sphere. It has a mass m, a radius r. This is a hollow sphere that has a mass m and a radius r. So this is a hollow sphere. This is a solid sphere. This is a cylinder, of course. And all of these have the same property, that the moment of inertia that is given is about an axis through their center of mass. So we will tell you how hard it is to rotate these things about an axis through the center of mass. Okay, so then maybe do this and this. Okay, so you're trying to do this, let's say. Moments of inertia will be given. You don't need to memorize them. I, center of mass, is equal to, in this case, if it's a solid sphere, it's 2/5 of mr squared. If it's a hollow sphere, it's 2/3 of mr squared. And then if it's a cylinder, a solid cylinder, it is 1/2 of mr squared. And so just like we said, these moments of inertia are a function of the mass of your object and its shape. Basically, the radius here is what counts. And we're going to give them to you because, each one has a different coefficient. So 2/5, 2/3, 1/2. I mean, you might even memorize them eventually because you see them so often, but the point is memorizing this has no real interest. So these will be provided, which is nice. I'll just memorize this guy, and then all of these guys I can deal with because someone will give me the moment of inertia. However, someone will give me the moment of inertia, but about the axis through the center of mass. Well, there's no requirement that every time a sphere rotates, it rotates about the axis through its center of mass. In fact, probably it's very easy to make sure that that's not what happens. So if these are given, then I have two options. Either I print a humongous phone book where I say, well, okay, the sphere for an axis about its center of mass is a certain moment of inertia, but then if the axis is here, it's another one. If it's here, it's another one. If it's here, it's another one. I just list off all the possible moments of inertia, which is completely ridiculous. It's not very practical. Or I find a way so that if you give me this, but in fact I'm not trying to rotate the sphere about this axis, but about one over here instead, then I can use I center of mass to find the new moment of inertia. Now that is called the Parallel-Axis Theorem. And it's not a very hard theorem to apply. The hard thing is to realize that you have to apply it, because it's very tempting to run with this if it's given, even though perhaps
it's not what applies. Okay?
So let's talk about the parallel-axis theorem real quick. Because it's a very simple theorem, but again, you have to realize that you need to apply it. So, and that goes back to the conversation where we said, well, torque net and I have to be computed about the same pivot. So you decide. But if the pivot that you choose is not the center of mass of the object, you don't get to use these. You have to move your moment of inertia using the parallel-axis theorem. Okay? So, the parallel-axis theorem says, okay, well look, let's imagine for a second that you have some object here that you want to rotate about an axis through its center of mass. And I don't want to draw anything special. I don't want to draw a sphere or a cylinder or anything. I'm going to draw Mr. Potato Head or whatever, like some shape. Okay, this is the center of mass, whatever. And you're saying, okay, this weird shape, maybe you want to rotate it about the axis through the center of mass. Okay, fine. Okay, now that would be you would then be given that moment of inertia, if that's what you're trying to do. Okay? Because the moment of inertia about the center of mass is going to be provided. Now, but maybe you don't want to do that. Maybe you want to rotate Mr. Potato Head around this axis here, which I'm going to call delta. Okay? And you want to swing it around delta like this. And again, I'm not responsible for figuring out physically how to rotate Mr. Potato Head about this different axis. I'm just being told this is what's going on, right? This is the axis of rotation I chose, or the pivot that I chose. I need to compute torque and moment of inertia about this pivot. Okay, well, I don't know what the moment of inertia about this axis is going to be. I only know I center of mass. Okay, so somebody gives me I center of mass for Mr. Potato Head. Okay. But if delta is parallel to the axis here on the left, which is a requirement, hence the name Parallel-Axis Theorem, and there's a distance d between these two, then the Parallel-Axis Theorem tells me that I, with respect to delta, is going to be I center of mass plus big M d squared, where, just to be clear, big M is the mass of Mr. Potato Head. Okay? So, this is a parallel-axis theorem. What it does, or what we say it does, is that it moves your moment of inertia from this axis here to this axis here. So if I give you I center of mass, you can actually find I delta if that's what you need to compute torque net equals I alpha. Now it's a very interesting theorem because what it does is I center of mass accounts for the mass and the shape of Mr. Potato Head. Just like up here, I center of mass accounts for the mass and the shape, the radius, of the solid sphere. So the shape of Mr. Potato Head is accounted for in I center of mass. But then we say, okay, well, we move from this axis to this axis, which effectively means that we took the entire mass of Mr. Potato Head and moved it out now a distance d to the axis of rotation. And we know that the further out mass is, the harder it is to rotate about an axis. How hard? Well, md squared, just like a point mass. So the added difficulty of rotating Mr. Potato Head about this axis is however hard it was to rotate about this axis, plus md squared, just like a point mass, because you move the mass m now a distance d from the axis of rotation. So the additional difficulty for rotating is just md squared. Anyway, great little theorem, very easy to apply. The hard part is realizing that you have to apply it. Okay, so don't forget the parallel-axis theorem if need be. Okay, so now let's move on to a couple of problems. I'm going to do first a pure kinematics problem. These are pretty rare because usually we like to
combine, everything we've learned into like a problem where you write torque net equals I alpha and maybe you find other stuff. But we don't usually just do pure kinematics with rotational motion. But let's do one just to practice and review kinematics and all that. And then we'll do an extremely classic problem, which we've done before, which is the Atwood machine. But this time it's going to be with a non-ideal pulley. In other words, a pulley that has a mass and a radius, and therefore a moment of inertia, and for which it is no longer true that the tension on either side is the same. And that's important because up until now, all of the pulleys we've ever encountered have been ideal pulleys, which is very nice. But now that we know about torque, we know about moment of inertia, it will no longer be the case that pulleys will be ideal. And so, well, they don't have to be, which means I need to know how to deal with a non-ideal pulley. All right, so let's look at this problem here. So you disembark from a helicopter, and at t equals 0, the blade is rotating at 10 revolutions per second, and then it slows to 6 revolutions per second after 10 seconds. And then eventually it will come to a stop. Okay, so we want to find alpha, the angular acceleration of the blade, during this 10-second period. And for approximation, we'll just take pi equal to 3. And then, assuming alpha remains constant, then when does the blade stop rotating? And finally, how many revolutions has it completed by the time it stops rotating? Okay, so let's draw this out to kind of summarize all the information that we were given. All right, so here we have t equals 0. When you disembark, the blade is rotating at, well, I'm going to call it omega 0, right? It's 10 revolutions per second. Now, careful, that's not the right unit. I need radians per second, okay? 1 revolution is 2 pi radians, so this is 20 pi radians per second. Okay, so that's omega 0. All right, then if you wait a little bit, this is going to be rotating, but not so fast anymore, so it's going to be like this maybe. This is t1 is equal to 10 seconds. And omega 1 is how fast it's spinning. And we actually know omega 1, 6 revolutions per second. So 6 revolutions per second, that is times 2 pi, 12 pi radians per second. Okay, so we know omega 1. Let's just say, for the sake of choosing one direction, let's pick counterclockwise. It doesn't matter, but okay. And then, by the end, when all is said and done, the helicopter blade is at rest. That's T2, to be determined, but omega 2 is 0. We know that. Okay. And we want to first find alpha. Okay, and we're going to make the assumption, just like we mentioned before, that, well, alpha is constant. Okay. So if alpha is constant, it's very easy to find it by looking at what happens between t equals 0 and t1 equals 10 seconds. Okay, we can say that alpha is just going to be the change in omega over the change in time, right? Basically, it's omega final minus omega initial divided by t1 minus 0. Okay, so that's going to be, well, omega final is omega 1, that's 12 pi, minus 20 pi, divided by 10, right? Well, that's going to be equal to minus 8 pi over 10, if pi can be approximated to be 3, just to get a quick answer here. 3 times 8 is 24. So this is minus 2.4 radians per second squared. Okay, well that makes sense. If omega 0 is positive, and I say that it's counterclockwise,
then alpha is negative, which means that it's clockwise, and that makes sense. Acceleration being in the opposite direction as velocity, or from velocity, means that velocity decreases over time. Okay, so that makes sense. Every second, the helicopter blade has an omega that decreases by 2.4 radians per second. That's what alpha is telling us. Okay, then assuming alpha remains constant, when will the blade stop? What is time t2? Okay, well, fair enough. I can solve for that because I can say, okay, here are my kinematic equations. And you're asking me to solve for time, so the only ones that involve time are theta t and omega t, right? So theta t is going to be equal to, well, I know alpha now. It's constant, so it's 1/2 alpha t squared plus omega naught t plus, well, theta naught. Now, omega naught we know, it's 20 pi radians per second. Theta naught, well, I mean, who really cares, right? If at t equals 0, theta naught is 0, then what I'm saying is that from t equals 0 onward, I'm counting for all the total number of radians that I'm accruing, that the helicopter blade is going to sweep through, right? Now, whatever that number is, let's say it's 100 radians, just to pick a number. Well, whether I count 100 radians by saying, well, I started at 0, and so now I've measured 100, or I start at 254, and now I'm at 354, doesn't matter. The only thing that matters is 100, right? So I can set theta naught to be equal to 0 because I don't care what theta naught is. I care what this is in terms of accrual of radians through which the helicopter blade sweeps. And then omega t is going to be alpha t plus omega naught. Okay, fair enough. How do I solve for t2, right? Well, I would say, what is true at times t equals t2? Well, omega 2 is 0. I know that for sure. And theta is going to be something, but that's question 3. Okay, so I'm just going to say at time t equals t2, omega is equal to 0. So I will say that at time t2, the blade stops and omega of t2 is equal to 0. Okay, well, what does that give me? Omega of t2 equal to 0 leads to alpha t2 plus omega naught is equal to 0. Okay, so it tells me that t2 is equal to minus omega 0 over alpha. Okay, that's minus 20, no, not, what am I doing? No, that's right, 10 revolutions per second, so that's 20 pi radians per second. That's fine. And then divided by alpha, which itself is, don't forget the minus, 2.4 radians per second squared. Okay, now this is going to be, if pi is allowed to be 3, 25 seconds. Okay, but don't forget that alpha is in and of itself negative. Okay, so that's going to cancel this minus. And that's how easy it is to find T2. Right? It's just when the helicopter blade stops rotating. So, okay, omega T2 is equal to 0. And then how many revolutions n will the blade make from t equals 0 to t equals t2? Okay, well, I need to figure out how many radians have I accrued between t equals 0 and t2 equals 25 seconds. That'll give me a total number of radians. Then if I want revolutions, I can just divide by 2 pi because one revolution is 2 pi radians. So what I'm going to do is I'm going to compute theta at time t2, which is going to be 1/2 alpha t2 squared plus omega naught t2, and that's going to be 1/2 times minus 2.4 times 25 squared plus omega naught is 20 pi times 25. And that's going to come out to, if pi is about 3, 750 radians. That's the total number of radians that the helicopter blade has swept through in 25 seconds, which is almost what I want. I just want the number of revolutions. Okay, well, easy enough. Yeah, the number of revolutions, capital N, is going to be theta at time t2, and because one revolution is 2 pi radians, we just divide by 2 pi. Okay, so it's going to be 750 divided by 2 pi, and that's going to be, if pi is allowed to be 3, 750 over 6, which is 125 revolutions. All right, so hopefully, it really mirrors what we did in kinematics before, and it makes sense how you would go about using kinematic equations for rotational motion. The math is the same, the process is the same. It's a different type of motion, I grant you that. But in both cases, we're looking for, to track position and velocity, and it involves acceleration. That could be linear quantities or rotational quantities, but the math works the same way. Okay, so that's for kinematics. Here, let's revisit an old problem, and we're going to find the angular acceleration of the pulley this time. Given that, yes, we have an ideal rope with 2 masses wrapped around this pulley, but the pulley is no longer ideal. Okay, now I know that because I'm told that the pulley has a mass m2 and a radius r2. Okay, now I'm no longer allowed to say tension on either side of the pulley is the same. It won't be, because if you try to rotate a pulley, let's say this way, well, the only way you do that is if this pulls on the pulley more than this, right? Because you need a net torque to rotate this thing, and it's now hard to rotate because it has a moment of inertia. So you need a net torque on the pulley now, whereas before we were allowed to have a net torque of 0 on the pulley. So what we're going to do is the following. We're going to take this thing and make a copy of it, and we are going to draw a free body diagram for each one of these objects, the pulley, but also M1 and M2. And we are going to say that there are 2 things happening. There's M1 and M3 that move linearly along the vertical. That's linear motion. If it's linear motion, well then linear equations are responsible for it. That's F net equals ma. Then the pulley is going to rotate. Well, that's rotational motion. Okay, so that's Newton's second law, but for rotational motion, so torque net equals I alpha. And then at some point, it has to all come together. Because the linear motion mathematically does not know about the rotational motion. They don't know about each other. They will have to know about each other because the rope never slips on the pulley. And we're going to see what that means in terms of acceleration. Okay. So let's start with the free body diagram for each one of these. We'll do the easy ones first. We'll do M1 and M3. M1 and M3, well, strings can only pull, so this is going to be T1. This is going to be M1G, downward. Okay. Then M3, strings can only pull. This is going to be T3. And this is going to be M3G. Okay. And by the way, M1 is greater than M3. So this whole thing moves where M1 falls, M3 rises, and M2 rotates counterclockwise. Okay. So this is just between you and I. M1 is going to accelerate downward with A1. M3 is going to accelerate upwards with A3.
I strongly suggest that you never draw accelerations on your free body diagrams, because you will probably be told, well, it's not a free body diagram if you draw anything else but forces. It should only be forces in a free body diagram, which, if we're being picky, is true. But if whoever's grading you is the one being picky, then we should probably humor them and not draw acceleration. But I find it very helpful. You can draw it and erase it later, maybe. But I find it very helpful to keep in mind, okay, M1 accelerates down, M3 accelerates up. It's going to matter when I write Newton's second law. Okay, but for that matter, M2 is going to accelerate counterclockwise. Okay, so alpha is going to be counterclockwise for M2. Now M2 is a little trickier. I have M2 and R2. I'm actually going to, let me get rid of these to not overcrowd the figure unnecessarily. Well, the easy part about M2 is that, okay, so strings can only pull, and it is an ideal string. So in the left portion of the string, the tension is the same everywhere. So pulls with T1 on the left side of M2. In the right portion of the string, it's an ideal string, tension is the same everywhere. So this is T3. Okay, that's still true. Okay, that this is T1 everywhere and T3 everywhere is still true. However, T1 is not T3. Okay, so now we have to have a little bit of a conversation. For the most part, if you look at answer keys, this is the free body diagram you're going to see. Okay, the reality is that, again, if we want to be picky, this means that there's a net force downward acting on M2, which means M2 has no choice but to fall. So there must be more forces in reality than just T1 and T3 acting on M2, which of course is true. First of all, there's a weight force, M2G. Well, that just made everything worse because now it's pulling even more downward. But there's an axle on this pulley, right? And the axle will exert force. You could call it a normal force. You could call it the force from the axle. Whatever, it doesn't matter. The point is that it's there, and it holds everything in place. So if you want to be picky, you would draw all four of these forces. But most of the time, you will see that we only draw these two. And that's because these forces here don't matter when it comes to the rotation. The force from the axle and the weight M2G go through the center of mass of my pulley. And that's going to be my pivot, so they're not going to create a torque about that pivot. So sometimes we just don't draw them. It's just like, yeah, it doesn't matter. So anyway, that's it. That's my little sidebar. But if you're worried, if you're wondering rather, like, why does sometimes we draw it and sometimes we don't? Well, it's kind of a shortcut. It's force of habit. We know they're not going to matter, so we're a little lazy. We don't draw them. But if you want to be on the safe side, draw them all the time. It's just they're not going to show up in the net torque. It doesn't matter. Okay, so then let's write some equations. Let's write Newton's second law for M1 and M2. Okay, we have to be careful with our signs here. Okay, F net equals ma. Okay, up is positive. Yes, that's what we're told here. Okay, so if up is positive for M1, I'm going to get T1 minus M1G, and don't go too fast, is equal to minus M1A1. Okay, that's why it's nice to draw A1. A1 is downward, so it's negative. M2, if I write F net equals ma, well, up is positive, so it's going to be T3. If I said M2, I meant M3. T3 minus M3, so hold on. Sorry. We're doing the blocks. We're doing the linear motion. So we're doing M1 and M3. M2 can wait. M3, sorry, up is positive, so it's T3 minus M3G is equal to, well, A1 is down, but A3 is up, so it's going to be M3, A3. Okay, so careful with signs. It's really easy to be off by a minus when you do this because of the direction of one acceleration.
Okay, so then we can write Newton's second law for rotation. That's going to be for M2 now. Okay, now that's going to say, well, torque net is equal to I alpha. Now I have to choose a pivot. I can choose any point I want to be the pivot. But what I'm given, just real quick, moment of inertia of the pulley about its center. So meaning that if I choose the center as my pivot, well, I just already know my moment of inertia. I can use it as is. All I'd have to do is compute the net torque about the pivot, which is doable. Now, it could make my life hard, and I could say, well, I don't want that pivot. I'm going to pick another point. I'm going to pick this point as my pivot. You're allowed to. It's fine. It looks weird because it's not really the true pivot for the motion, but mathematically you can do it. But now you have to compute torque net about that pivot, and you have to compute moment of inertia about that pivot, so you got to do Parallel-Axis Theorem. So, okay, as fun as that might be, you know, if I'm taking an exam, I don't have time to play around. I'm going to use the center of mass as my pivot because like that, I already know the moment of inertia. I just have to compute the net torque, which, by the way, is going to be very easy to compute because the two forces that I don't know or don't really care for mean F axial, which I actually don't know, and M2G, which I do know but I don't care for, go through the pivot so they don't create a torque, right? So remember we said torque net last week is the sum of all the torques. It's going to be torque of T1 plus torque of T3 plus torque of M2G plus torque of F axial. And all of that is going to be equal to 1/2 M2 R2 squared times alpha. Okay, but these two are going to be 0, okay, because M2G and F axial are applied at the pivot. Okay, so there's no distance between the pivot and these forces, so they don't create a torque about this pivot. In other words, the only way you get a rotation is with T1 and T3. You can pull down like this with M2G. It's not going to cause a rotation one way or the other about the pivot. It's just not. Okay. So, fair enough. Then what is the torque of T1? What is the torque of T3? Okay, this is my center of mass. Now I need to know the distance between my pivot and my force times the force sine of the angle between the two. Okay, well that's pretty easy. Okay, the distance between the force and my pivot is going to be equal to the radius R2 of the pulley. This angle will be 90 degrees here. Okay, that's because T1 is tangent to the pulley and therefore perpendicular to the radius. If you're not convinced, grab a toilet paper roll. You can pull on the loose leaf from any direction. You will see that at the contact point, the point of where it's tangent, the sheet of toilet paper is perpendicular to the radius. Okay, and so same thing here, right? Meaning that I'll just write them here and then I'll bring them down with me. But torque of T1 is going to be, now I forget all the other forces but T1. If I pull along T1, this is going to rotate counterclockwise. Okay, counterclockwise is positive, so this is a positive torque. It is distance R2 times force T1, sine of the angle between R2 and T1, which is 90. Torque of T3, well, if I forget all the forces but T3 is going to pull like this and try to rotate the pulley clockwise. That's negative. Okay, and then distance R2, force T3, sine of the angle between R2 and T3, which is 90. Okay, so I'll bring these guys with me. Okay, and I'll just leave them here for now, and we're just going to rewrite torque net equals I alpha. It's going to be R2 T1 sine 90 is 1 minus R2 T3 is equal to 1/2 M2 R2 squared alpha. So this is going to be R2 T1 minus T3 is equal to 1/2 m r2 m2, sorry, r2 squared alpha. And of course you can cancel r2 and the squared. You get t1 minus t3 is equal to 1/2 m2 r2 alpha. Okay. Now, by the way, this is why, if we have an ideal pulley, which is massless and frictionless, T1 is equal to T3, because M2 is equal to 0. So we didn't know that. We didn't know why T1 was equal to T3 if I had an ideal pulley, but it comes from the fact that it has no moment of inertia. Right? And also there's no torque from friction on the axle that would add a torque here. There's just T1 and T3 creating torque. If there's no moment of inertia, T1 will be T3. Okay. But now that's no longer necessarily the case, so we have to account for the fact that there is a moment of inertia, and we have to figure out how all this plays nicely together. Now we've done, in a sense, we've done the hardest part. The hardest part is to say, okay, look, for linear motion, that's M1 and M3, I have to write this. For rotational motion, that's the pulley, I have to write this. These equations do not know about each other. Right? The Newton's second law for linear motion has no clue that we wrote Newton's second law for rotational motion and the other way around. Okay, because there's nothing that connects them. Right? So okay, so we have equations, right? I mean, we can say we got, let's just summarize what we have. We got T1 minus M1G is equal to minus M1A1. And then we have T3 minus M3G is equal to M3A3. And then we have T1 minus T3, sorry, is equal to 1/2 M2 R2 alpha. All right. And so you might say, well, I mean, don't they know about each other? Because we have, T1's in here, T1's in here, and T3's in here, T3's in here, so aren't they all connected? It's like, well, sure, in a sense, yes, but they don't know about each other, meaning that they describe different types of motion, and there is, at the moment, no relationship between the linear motion and the rotational motion of the pulley, which, in reality, there must be, right? It must be the case that how heavy M1 and M3 are dictate how fast the pulley rotates with time, right? So there has to be a relationship between this motion down, this motion up, and this motion going around like this. So what is that relationship? Well, that relationship is the no-slip condition of the rope on the pulley. Okay. So if the rope never slips on the pulley, right? So in other words, you don't allow the pulley to remain in place without spinning, and then the string unravels, the rope unravels. That's not going to happen. Right? You think of it as a bicycle chain with the sprocket or whatever, the gear, and as you pull, there's a proportionality between how much chain you pull off and how much rotation you get. It's exactly the same thing, right? And so what happens is that if this is the rope right here, I'll do it on both sides for that matter, then how fast the rope is coming off, which we'll call V3, or that's V1, so sorry, V1 for M1, how fast the rope falls versus how fast the rope is being pulled up like this, that would be V3, has to be related to how fast the pulley spins, right? And it turns out that V1 is going to be equal to V3 is going to be equal to R2 times omega. Okay, that's the no-slip condition. The no-slip condition, in terms of speeds, doesn't really help us because we have accelerations, but it translates to acceleration as well, because if this is true at all times for velocity or speed, then it has to be true for acceleration. It has to be that A1 is going to be A3 is going to be R2 times alpha. I mean, all you have to do is take the derivative of this, right? If you ddt this thing, dv1 dt is a1, dv3 dt is a3, and r2 omega becomes r2 d omega dt, which is r2 alpha. So this is the no-slip condition for the rope and the pulley. And typically ropes never slip on pulleys in this class. Okay, so there's a proportionality between how fast M1 falls, M3 rises, and the pulley spins, which makes sense. Okay, so if that's the case, then we ought to be able to solve for alpha, because that's what we want to solve for at the end. So we can do this. We can update our equations. We can say, okay, well, I'm going to write this as T1. I'm going to say T1 is equal to M1G minus M1A1, which is really R2 alpha. T3 is equal to M3G plus M3A3, but that's R2 alpha. And then T1 minus T3 is equal to 1/2 of M2 R2 alpha. I'm going to leave it like that because I am solving for alpha. Right? But now that I have that, okay, I can substitute T1 and T3 into the last equation. So I can say that T1, which is this, minus T3, which is this, is going to be equal to 1/2 of M2 R2 alpha. Okay, so I'm going to get M1G minus M3G minus M1 R2 alpha minus M3 R2 alpha is equal to 1/2 M2 R2 alpha. So I'm going to put on the right-hand side all the terms that contain alpha, factor out alpha, and divide. So I'm going to get M1G minus M3G is equal to M1 plus M2 over 2 plus M3 R2 alpha. And I could multiply everything by 2 if I want to get rid of the half here, or if I don't really care, then I just do this. Okay, so it's M1 minus M3G, because I can factor that out too, divided by all of this. And that's going to be alpha. Now it turns out I have all the values I need to compute this thing. Right? So M1 is going to be 7, M3 is 4, G is 9.8, divided by 7 plus M2 is 2.5, if I recall. Do I believe that? Yeah, 2.5, that's right. 2.5 plus M3 is 4 times R2, which is 0.5. Okay, and this is about 4.8 radians per second squared. Okay, now of course, if I know alpha, I also know A1 and A3, which means that if I want, I can go back and solve for T1 and T3 because now I know everything. And as is typical of these types of problems, like we mentioned before, usually once you get acceleration, you can find everything else, right? So even if the problem were phrased differently, let's imagine it's the same problem, but now instead of being told find the angular acceleration of the pulley, I'm just told find the tension in the string everywhere. So in other words, find T1 and T3. Well, I would do the exact same thing, and I would make it up to here, and I'd find alpha. I would then solve for A1, A3, and get T1 and T3. So changing the question doesn't really change my approach here. I would still want to get either A or alpha first, and then I'll know both A and alpha. Then I can go back to these equations, and I can compute T1 and T3. But without acceleration, I can't do it. So usually my first step in these types of problems is to compute acceleration. So, just taking a step back. Last week we said we're going to talk about a new type of motion that we have not encountered before, which is rotational motion. It's different because we can no longer treat objects as point masses. We have to treat them as extended bodies that have a shape and a size. And where the force is applied is now going to matter. So we started drawing extended free body diagrams. We defined torque. And we said, well, to get equilibrium to still work, we have to add torque net equals 0. This week we said, okay, well, not everything in life is in equilibrium. Some things like pulley are actually designed to not be in equilibrium and to spin or rotate. So how fast do they rotate, right? Given a certain mass and a certain rope wrapped around it and so forth, or something like that. And then we had to say, okay, well, first of all, we need to describe the rotational motion. That's kinematics. Then we have to figure out how to get alpha from the torque and the moment of inertia, which prompted us to define the moment of inertia. So we recycled old stuff from last week, torque net, but added a few more things, I alpha, to describe this rotational motion. And next week we're going to move on to a third type of motion, or well, the third part of the chapter, and a new type of motion, which is rolling without slipping. Now a lot of the foundation has been built already, so we're not going to add that much more stuff in terms of equations. Most of the equations we need we already have, with the exception of conservation of energy and kinetic energy of rolling without slipping. So we're going to define rolling without slipping, and then we're going to show that we can just look at let's say a sphere rolling down an incline, and we can use torque net equals I alpha, F net equals ma, kind of like we just did here, and that'll be the bridge between this session and the next. And then we'll say, okay, well, fine, you could do it that way, but you could also do it with conservation of energy, and we'll do conservation of energy. And of course, that's a lot faster, assuming what you're solving for can be derived from conservation of energy. So trying to make progress through this chapter in the same way that we progressed through the previous chapters when we were talking about linear motion, because I think that's the most logical way to go about it. So again, I realize that's different from the order done in lecture typically, but as long as we do all three before the exam, then you can just follow in order. Probably be a good review for what you've already learned in lecture anyway. And then you can go do the practice, and you'll see it's not that bad if you realize the different compartments that you have to deal with, and that equilibrium, of course, is not the same as rolling without slipping, and you have to kind of separate everything to know what to write and how to write it. Anyway, so we've done 2/3 of the torque chapter for now. Next time we'll do the last third, and from there we will move on to a whole collection of chapters that are kind of standalone. Fluids being the most remarkable one of them all. Fluids is super straightforward, it's really nice, but it's kind of its own thing. And all the next chapters are it's kind of a collection of things that you have to know, but it doesn't all fit together nicely like everything we've done up to this point. So that's fine. We'll just go through it. It'll feel a bit more plug and chug and like a checklist that, this, and this. But that's how the class is structured. So just pointing out that once we finish torque, everything from day one to the end of torque kind of fits nicely together. It's all of mechanics, and you can see analogies and parallels, and you can see that it kind of is one big whole. After that, it's no longer the case, but that doesn't mean it's bad, because we just have these little chapters we have to get through, and they're not terrible. Oscillations, so-so, but the rest is pretty straightforward. So anyway, we're getting close to the end, but we're certainly getting close to midterm 2, so good luck studying. I hope everything is going well. And I will see you next week to finish the torque chapter. Have a good one. Take care.